Hi guys, we're group 3 and we'll be presenting on counterfactual generative networks. We'll begin the presentation by doing a quick recap of the original paper. The motivation for this paper was trying to increase the robustness of image classifiers. This came about because the authors noticed that image classifiers tend to learn spurious relationships between elements in an image. An example of this would be if I have a dataset of images, and every image with the label cow has a cow in a green field like the cow on the left. While the classifiers will perform well on images like the middle one, it is likely not to perform well on images like the one to the right. This happens because it is possible the classifier has learned a spurious relationship like the one between a cow and a field. Because the last image violates this relationship, despite it being a valid image of a cow, it is misclassified. To address these types of problems, the authors proposed the counterfactual generative network, where classifiers will be trained on images in a variety of contexts. The model will first generate counterfactual images based on the real image and change elements like the shape, texture, or background. After these counterfactuals are generated, 3 classifiers will be trained on the generated images. 1 classifier for shape, 1 classifier for texture, and 1 classifier for background. Now, we'll talk about the motivation for our experiments. We observed that the 2 datasets used in the paper are the MNIST and ImageNet datasets. The model performs very well in these datasets, but we noticed that these datasets are made up of images that contain a single subject, like a plane, a dog, a single number, like 0 or 2, and have classes such that things that are not in the same class look fairly different. So we wondered how well the model will perform on a dataset where this is not the case. We now present our research question. How will the counterfactual generative model perform on a dataset that includes samples that share similar shapes and have disjoint or non-continuous structures? Here are some sample images from our dataset, which demonstrate the disjoint and similar shape properties. On top, we see images with similar shapes but different classes. On the bottom, we see images with the disjoint property. We'll talk more about the dataset shortly.
Hello, my name is Matt Harris, and I'm going to go over the learning model. So we're going to start with a high-level overview here. So to read this picture here, the blue shapes are pre-trained models, and specifically here, these are these big GAN models that are in blue. The trainable models here are in green, and you'll see there's a couple U2 nets, and there's a big GAN at the bottom, part of the CGAN. So how this model works is there's 3 independent mechanisms, and that is F-shape, F-text, and FBG, which is background. And the output of those is input into the composer, right? So the independent mechanisms, for example, isolate the specific invariant, which is like shape, for example. And once it's all isolated, you can generate them using noise and then compose them using a composer at the end. This big GAN at the bottom that's outside of sort of our model here is just used for the supervised training. So let's go into what an independent mechanism really is. So let's talk about U2net. U2net is another model that's used to split an object from its background. And so our independent mechanism for shape uses this U2net to generate a mask, right, which is this black and white image. Now our composer here uses compositional image synthesis, and it uses that to sort of put those things together. So it takes a shape, and it takes a background, and it puts the shape on top of the background, and then gives it the texture. And this composer is analytical rather than learned, which means it's not modeled, it's not a neural network. It's based on this compositional image synthesis, and it's a mathematics which is based on alpha blending, right, which puts it all together. Now our invariant classifier, so we have our CGN, which generates counterfactuals, and then we need to use our counterfactuals to train an invariant classifier, right, to do our image classification. It uses a convolutional neural network, right, and when we talk about the testing later, we also have these other models, right? We have IRM, which is invariant risk minimization, and we have learning not to learn, which are similar models and similar research to this, which revolves around removing some biases based on the training.
The hypothesis we have formulated is the fact that the CGN model will stay fairly accurate despite limited shape variation or discontinuity in the structure of the samples. And we believe that will happen because the model learns a generalizable shape context along with the independent training classifiers. Now let us take a look at our experiment design. Now, if we consider the data set we are using for this experiment is the Chinese MNIST data set. Here we can look at a preview of the data set on the left side. This was an open source CSV format data set available on Kaggle. It comprises of 15,000 samples in total. Since we have performed a 80-20 train test split, which gave us about 12,000 samples to train our model on and gave us about 3,000 samples to test our model on. It contains about 10 distinct classes of Chinese characters. As we can see for the modifications made to the model, the step one was preparing our data. As we can see here, the data format we were working with was a CSV file with 64 columns containing the intensity value for each pixel. We needed to convert the dataset into a dictionary containing the train test images and labels as the key and the pixel values in an ND array format using the pandas and numpy library. Since we were using grayscale image data, we converted the same to an RGB array similar to the one being used in the paper. Also, the labels were converted to arrays of value arrays. For the step 2, we were tuning the hyperparameters. For this, we performed a grid search on the hyperparameters of the model, like the number of epochs, the batch size, the gamma values, and the learning rates in order to find the values that would give us the best possible accuracy for the model of our dataset. And finally, in order to train the classifier, we defined an initializer function that loads the Chinese MNIST dataset from our preprocessed numpy file and assigns the image and label data to the corresponding instance variables. We also generated weights similar to the ones provided in the paper, since the data we were handling was of a similar type. The loaded images were then transformed using the PyTorch library, which resizes them to a 32 by 32 pixel size. Finally, we also modified the train classifier and generated data to accommodate the new option for data and modified their argument parsers and dataset checks to include our Chinese MNIST data.
As you all now know, this model has several steps. We trained the CGN on a dataset to generate counterfactuals. We then generated those counterfactuals, and finally we trained the shape classifier on this new dataset. The above table are the results of our grid search over possible values of learning rate and gamma for training the shape classifier, the last step of the process, and the step that gives us our metrics for judging the model. These were all run for 10 epochs and gave us an idea of the ideal values for training. Since we were focusing on test accuracy, we decided to go with the learning rate of 0.1 and gamma of 0.01. With these values, we trained the classifier again with a batch size of 100 and for 30 epochs, and got our final results shown in the bottom table. The shape classifier, when trained on the Chinese MNIST counterfactuals, had a much worse accuracy than when used with the other MNIST datasets, all of which had a test accuracy of above 85% compared to our 15.35%. This disproves our hypothesis that the CGN would remain robust and train the classifier similarly well to the other datasets. Let's explore why. We have several theories on why the CGN may have performed much less well with the Chinese MNIST set. On the right is a comparison of the mass generated by the models. The left screenshot is generated from the wildlife MNIST dataset, and the right is generated from the Chinese MNIST dataset. Our counterfactuals are much less clear to make out and have some interesting unexpected features with them, although the Chinese character for 0 is somewhat discernible. One reason that could have played into a worse accuracy was the interpolation step we had to use to fit the data to the model. While for the colored MNIST the figures were 28 by 28 and had to be scaled up slightly, our data had to be scaled down by 50%, a much more significant margin. We believe the main reason that the model performed worse is the nature of our dataset. The characters are largely disjoint, much more complex than Arabic numerals, and our backgrounds are quite dark with thin lined characters. All of these factors could play into making it harder on the model to not only generate reliable counterfactuals to be used in training the classifier, but also to classify the data with the exceptional accuracy we've seen with the wildlife MNIST, colored MNIST, and double colored MNIST datasets. And here are the references we used for our paper and presentation.